Good evening. This is Boaz Arberg back with you on MET 415. What we'll do in this presentation is a look at Mathcad Operations. We will start with a Mathcad download. We'll see how we can get it on our system. We'll look at the vector algebra example and an example of matrix transformation. To download Mathcad, you can go to Bing or Google and just type Mathcad download, and you'll come into the page of ptc.com, and you'll see that if you don't want to use student edition, you can pick up the Express, and the Express, according to Mathcad, is free for life. It says right here, Express is free for life. So once you load it, you could go through the basic operation, such as multiplication of vectors, both dot product and cross product, and matrix transformations, which are very useful in robotics. This is an example of a typical problem where we have a robot link which has a center of gravity at a certain point in an x, y, z coordinate system. And the distance from the pivot to the center of gravity is defined by vector r. You see it has components over here of 1,000 millimeters in the x direction, 300 in the y, and 200 in the z. And there is a point, at the CG point, there is a force, inertial force, which acting in this direction. To find the cross product, we translate this force to the origin of R, and the cross product will be the vector which is perpendicular to both and oriented as a right-hand screw will advance. And it is shown right here as a torque which is equal to the cross product of R and F. And you see that the cross product has various components, so we may be interested in finding the torque along the y-axis, and this is the component because that particular torque may be the torque that the motor will have to provide in order to generate this force at this location. The other components of the torques will be bearing reaction that will be used to calculate bearing life or bearing strength or stiffness or deflection, deformation, so they also have use in robotics. To see how Mathcad is handling the cross product, we have R over here defining the components in millimeters. We put the units. We have over here the force in newtons. This particular one was 200, 1,500, and 500 based on the scale. And when you take the cross product with a simple notation of R cross F and assign it to T, you immediately get the component of the torque. And as you see, it's minus 150 in the x direction, minus 460 in a y direction, and 1,440 in the z direction. This is the value of the torque, and is given to us as Newton meter or simply joule. Now the magnitude of these vectors is also given by the norm of the vectors, designated by two bars on either side of the vector, and Mathcad calculates it immediately. Here we see the distance from here to the CG is about 1 meter. The force is 1,594 newtons. This is the total force from here to here, and the torque is also given to us in joules over here. And if we want now to project this torque along the y-axis, we take the dot product of the torque with a unit vector along the y-axis, which is 0, 1 in the y direction, and 0. And the result is given to us as minus 460 joule, which is exactly the component over here of this torque vector. Now, to find out the angle between them, we can either use the cross product definition or the dot product. If you use the cross product definition, you see that alpha can be found by taking the magnitude of the torque divided by the product of the magnitudes of the two vectors. This is designated over here with this formulation. And to convert the angle from radians to degrees, we multiply by 180, divide by pi, and we get 63 degrees, 0.724. If you use the dot product designation, you see that alpha can be found by the arc cosine of the dot product of the two vectors, which is a scalar, divided by the products of the magnitudes of these two vectors, and this is designated over here, and we ended up with the same angle. So this is an example of how we do cross product and dot product with Mathcad. A more interesting example here is coordinate transformation. Suppose that now we want to take the vector t, which is defined now with components resolve in x1, y1, z1, and suppose that we like to find the components of the same vector along x2, y2, z2 coordinate system, and the coordinate system 2 is rotated with respect to coordinate system 1 along the y2. You see that x1 is rotated over here, theta, to get x2, and z1, not shown, is also rotating an angle theta. They keep themselves still orthogonal to each other. So to do this, we will define the vector t in coordinate system 1 as t1. It's exactly what we had before. And we will define the projection of t on system 2 as t2. Now the question is, what will be the transformation matrix? Okay, to look at the transformation matrix T12, which takes a vector which is represented in coordinate system 1 and transform it to coordinate system 2, we have to determine the values of that matrix. Now over here we see the two vectors. It has a component in the first coordinate system Rx1 and Rz1. This is Rx1, Rz1. And we want to find out Rx2 and Rz2 with the transformation matrix. You see that the positive rotation of the second coordinate system with respect to the first one is in this direction, and we find out by using the right-hand rule, going for z1 to x1, my thumb will point in the positive direction of the axis of rotation, which is y1. Now, to build up the transformation matrix, we take the axis of rotation and we place on a diagonal of the corresponding axis 1. We put zeros on the column and the row which correspond to that axis of rotation. We put cosine on a diagonal, cosine of the angle, on all the other axes. And on a cos diagonal, we put the sign. One of them takes the minus sign, but if we follow the right-hand rule convention, it'll be up on the upper right hand. And we could also check it because Rx2, this is the component that we're looking for, is equal to the value of Rx1 times cosine of theta, we see here, and we have to subtract from it this much in order to get this value. Now, this value is the Rz1 times the sine of theta, which will be this component over here. So if we take this value, subtract from it this value, then we will get Rx2. So Rx2 equals to cosine theta times Rx1 minus sine theta times Rz1. So this checks. We can use this check to this sketch to check the matrix of transformation, and we can do it no matter what is the combination of x and y, or y and z, or z and x. When we rotate about a certain axis, we use this convention. We now can use this transformation matrix, copied again over here, to see what will be the components of the vector t, which is the torque vector that we found earlier, r cross f, when looked by an observer which is located in coordinate system 2. Coordinate system 2 again is rotated in positive direction about the y1 axis, and we also see that the z is rotated, but the y stays the same. y2 is exactly the same as y1, only x2 and z2 rotate with respect to x1 and z1. Now, we can build in Mathcad the matrix of transformation. We can denote it as T1 underscore 2. We put the values the same way as we found them earlier. Cosine theta 0 minus sine theta 0, 1, 0, sine theta 0, cosine theta. We can define the vector of the torque in coordinate system 1. Before we called it t. Now, when we have two coordinate system, we'll call it T1. We'll assign the old values, here they are, and then to find out the reflection of this vector in coordinate system 2, we take this transformation matrix and multiply times the vector t as shown in coordinate system 1, and the result will be the same vector result in coordinate system 2. We can double check that, and we see that in coordinate system 2, this vector will have a component along the minus x2 axis. It's minus 849.9. It also has a negative component on the y2 axis, which is minus 460. It is the same as it was before because the y has not changed. y2 is the same as y1. And then we can also see that if we take this vector and resolve it along the z2, we put the perpendicular line here. This will be the resolution along the z2. We see over here that it's in a positive direction, and the value is 1,172 joule. So this shows us how simple it is to make the matrix transformation with Mathcad. We assign a value to theta of 30, and automatically we get all these numerical values. We'll use in upcoming presentations the Mathcad in order to do some calculations related to robotics. Thank you.